Hello everyone, my name is Wang Dongkun and my partner is Wang Guangtai. Our research topic is low resources machine translation. Our presentation has 5 parts. The first is introduction and goal. The second is related works about NMT. The third one is methodology about low resources machine translation. The fourth one is experimental results and discussion. The finally is conclusion. First, I want to introduce our introduction and our goal. Model used technologies. Well, we have used word embeddings, attention mechanisms, and the sequence-to-sequence model. The most important part in our research topic is the transformer model. And it is well known to everyone that transformers take a lot of time to be calculated. Evaluating method. Our system will be evaluated on a separated blind test set based on the bilingual evaluation and the study score, and we have used this style for standardizing handling of tokenization process. Finally, the goal. Our implementation is a neural machine translation, namely NMT system, and it is capable of translating English into French using 11K aligned examples and 2 unaligned monolingual corpora, 474K for each language. Now I want to introduce some related models about NMT. The first one is recurrent neural network. It has the advantage to capture long-distance dependencies in language, but it also has some problems about vanishing gradient. The second one is encoder-decoder model with attention mechanism. The decoder in it can rely on all input vectors by using powerful attention mechanisms. It increases translation accuracy and makes it easier to tell which words are translated into which in the output. The third one is transformer model. Transformer can improve the sequence-to-sequence modeling through the self-attention mechanisms and the positional encoding mechanism. And the translation quality is better because it requires less computation. The fourth one is bidirectional encoder representations from transformer, and its major contributions lies in the deep bidirectional nature of its architecture and its novel pre-training task. The last one is back translation. It converts monolingual target into the source language, providing syntactic source sentences as additional training data. Now I will introduce our data preprocessing flow. First, we will strap sentence and add tokens. Secondly, we will lowercase our sentence of unaligned English data. Third, we will add space for unaligned French data in order to easily separate the tokens. And finally, we will perform an 80-20 split on the raw data to ensure that the validation dataset is not included in the English input data. Now I will take a brief introduction of word embeddings. Word embedding represent words being mapped to vectors. Secondly, we experimented word-to-vector mechanism with embedding size of 128, meanwhile 254. Certainly, we pre-trained a Roberta model on the unaligned English samples and used it as an embedding layer in a encoder-decoder architecture.
Next, I want to talk about encoder-decoder gate recurrent units with attention. This sequence-to-sequence model uses GRUS as its encoder and decoder, and implements attention to alleviate the bottleneck issue of information from encoder being compressed into unhidden state and passed on to the decoder. During the training, the input is passed through encoder, which returns an encoder output of shape and an encoder hidden state of shape. The decoder returns predictions and decoder hidden state, and predictions are used to calculate loss. Third, teacher force is used to decide the next input into the decoder. Gradients are calculated, which are applied to optimizer and back propagate throughout the model. As for transformer model, the input sequence is passed through encoder layers that it generates an output of each word token in the sequence. The decoder attends on encoder's output and its own input to predict the next word. During training, this model uses teacher forcing, where true output is passed to the next side step regardless of what the model predicts at the current time step. Cross-entropy loss are used, and padding in the sequence was not used to calculate it. And last is iterative back translation. Firstly, training with authentic data only that provides a baseline. Secondly, training with only synthetic back-translated data, which scores keep rising. Lastly, training with combination of the authentic and synthetic data, it was discovered that increasing authentic from 1 million to 3 increased BLEU score by 7.4%. Adding large amount of synthetic data increased score by tops out quickly. This is our result. You can refer to the table. This table shows the result of using different transformer model sizes with and without using word-to vector embeddings. Model use word-to vector performed marginally better than those without it, and the result of the robot A model was worse than word-to vector due to the small training size used with existing aligned samples to train original French English task. BLEU score was 10 when the ratio of original aligned samples to that of synthetically generated data was 1:1. Adding synthetic data to the mix and the scores keeps improving. Iterative back-translation can further improve French-English model to generate quality synthetic samples. At last, we can draw a conclusion. In this project, we investigated the performance of an English to French NMT system using models with different architectures. Large amount of back-translated synthetic data to increase the training size. That improves the scores. Translation performance improves with additional synthetic data. Performance tends to saturate when balance is tipped too far in favor of synthetic data. And there are some future work. Beam search decoder would be preferred over Grady, and the multitask system could be useful when BERT is trained on masked modeling and stimulously improved by joining it with decoder for translation task. And we could explore various other tokenizers such as bytes processor ones. That's all. Thank you.